So we are looking at TCP versions. We already finished TCP Tahoe. TCP Tahoe has some fundamental drawbacks in that it is slow to recover from losses and it acts on timeouts to detect losses. So during timeouts, the pipe is drained and then you're forced to do slow start, which takes additional time to fill up the pipe. So the TCP Reno incorporates two new mechanisms to handle this. So one is fast retransmit and another is fast recovery. Fast retransmit is very simple. It is now going to rely on these duplicate acts to figure out that something is lost. Basically, if it receives 3 duplicate acts, it is going to conclude that that packet is lost. Now, if you are wondering why 3, why not 1 or 10, what do you think? Are the reasons for this? If you receive just one dupack and you conclude loss, if the packets were reordered, then as I said, this is not maintaining conservation. That is, you're putting a packet before the packet was removed from the pipe. You could wait for 10, but this is way too many. There may not be enough packets out there to generate this 10 duplicate acts, and this more or less boils down to the timeout event. So a good compromise is some value in between, and they chose a value of 3. So this is more or less like a timeout event. So when you receive 3 duplicate acts, you assume that the packet is lost, you retransmit the packet, and you know that the packet is lost due to congestion, thereby you cut the window by half. By the way, this doesn't mean that there are no timeouts. Timeouts are the backup mechanism. So this way you avoid having to time out, which keeps the link idle for a longer duration. Now you're acting much faster. The other mechanism which TCP Reno employs is fast recovery. This is to avoid the pipe getting empty. Let's see how it works through an example. Suppose you're entitled to a window size of 25. Of course, the sender doesn't know about this. So it starts with slow start. It will start with 1. It will increase it to 2, 4, 8, 16 and then 32. This is going to drive the network into congestion. You detect the congestion through the duplicate acknowledgements, and then after 3 duplicate acknowledgements, you are going to retransmit the particular packet and you're going to wait for an acknowledgement. So this act will come after some time. Now during this time, you will still be receiving more dupacks. So fast recovery does something clever by utilizing these duplicate acts to ensure that the pipe doesn't go empty and thereby preventing the need to do slow start at this point. So during this phase where you retransmitted the packet till you get an acknowledgement for that packet is where fast recovery phase lasts. So what is the idea here? The fact that you are receiving duplicate acknowledgement means that the receiver is removing a packet from the pipe, in which case it makes sense for you to put a packet in the pipe in place of the previous packet. That way the pipe doesn't go empty. And then once you receive an acknowledgement for this retransmission, from this point on, you can do the congestion avoidance. In this particular example, operate at that safe operating point of 16. So this is how fast recovery is implemented. Once you receive the 3rd dupack, you're going to retransmit the packet and then you're going to cut your window by half, that is here, and you set this SS thresh value equal to this max of this. Where is this 2 coming from? Well, frankly, I don't know the origins of it. Whether it is 1 or 2 hardly makes any difference. Well, in any event, this is what the standard says, but in most cases, this is what you're going to act on. This is a subtle point. Since CWND is what is going to dictate how many packets you can send, you are going to artificially inflate it by 3 to account for the fact that you have received 3 duplicate acknowledgements so far. That is, since 3 packets have been removed, you can potentially send 3 more packets that you achieve by artificially inflating the window in this fashion. This happens only during this fast recovery phase. What happens in this specific example is you're going to set it equal to 19. Note that this is being done only to ensure that you can send packets in response to these duplicate acts. Your safe operating point is still 16. And during this fast recovery phase, for every DOPAC that you receive, you're going to increment it by 1 to ensure that you can send one more packet in response to the duplicate ACK if the window permits. And once finally this acknowledgement comes, that is, this is acknowledging new data, you are now going to go back to the safe operating point. In this example, you'll go back to 16. And then you invoke congestion avoidance, which is the linear increase in CWND now on. I know you need an example to understand this. I will get to that. But before that, so this is how the window evolves in case of TCP Reno. So this is the slow start phase. And after some point, this is determined by SS thresh, it does congestion avoidance. And at some point, it is going to hit congestion. So at this point, it cut the window by half. As you can see, the slow start phase is missing here. You are just doing congestion avoidance after this. Now, if you are wondering what this portion is, sometimes TCP Reno, when there are multiple losses within a window, has to time out. So this happened mainly because of a timeout. In general, this is the behavior. It avoids slow start. Here is a quick comparison with TCP Tahoe, which highlights the differences. So as you can see, until this portion, everything is same. After this, where you concluded a loss, in TCP Reno, you are cutting the window, but you are avoiding slow start and just doing congestion avoidance, whereas in TCP Tahoe, you are cutting the window to 1, doing slow start. So this is the slow start phase until this SS thresh, and after this point, you do congestion avoidance. As you can see, TCP Reno does better than TCP Tahoe. So here is the promised example. So here is TCP Reno. We are working with the same setup as before, in that we are assuming that the packet 14, 26, 28 were lost, and until this point there is no difference between the TCP, Tahoe and Reno. So here are the duplicate ACKs that are coming asking for 14. So this is generated as a consequence of 15, this is generated as a consequence of 16, this is generated as a consequence of 17. So these are the 3 duplicate ACKs. So as a consequence of this, you're going to now retransmit 14. So this is the fast retransmit. Then you're going to enter fast recovery phase, where you set SS thresh equal to 7. And what is CWND set equal to? 7 plus 3, that is 10. So this 3 accounts for the fact that 3 packets have been removed from the pipe. Now, when you receive the next duplicate ACK, which is being generated by this 18, you're going to increment the congestion window. So now it is CWND is 11. By the way, this is an artificial inflation. Can you send any packets as a consequence of this? For that, you need to figure out how many packets are actually outstanding in the network as far as the sender is concerned. Well, you sent packet 14. And then there are packets 15 to 28 whose status you have no idea about. So there are overall of 14 plus 1, 15 packets out in the network. So that's what I'm representing here. I'm giving it number 1 that matches here. So there are more outstanding packets than what your window size is telling. So thereby you cannot send any more packets. So as more ACKs come, you're going to increment this CWND. At what point can you send the next packet? In other words, what is this value here? That, if you did the calculation, turns out to be 23. So as more and more ACKs come, you keep sending these packets. So what is the sequence number of this last packet that you can send as a consequence of these duplicate ACKs? Well, you're not going to get an ACK for 26 and 28. So you'll get for 24, 25, 27. So you can send 3 more packets, or maybe I should just specify like this. So it is 29, 30, 31 and 32. So this is in response to 24, 25 and this is in response to 27. At this particular point, what is your value of CWND? This, if you did the calculation again, is equal to 19. After this point, there are no more acknowledgements coming from before. There is only the acknowledgement pending for 14. So that is what comes here. And what is this going to ask for? 26, right? Because that is lost. So at this particular point, you are going to exit the fast recovery and set your CWND equal to 7, which is the SS thresh value that you stored here. So after this point on, you should be doing congestion avoidance. But now the next acknowledgement that is coming is still asking for 26, which is being generated by this 29 packet. But then this is a duplicate ACK, so you cannot increase your congestion window by 1 over CWND. So you wait. You are now going to get another duplicate ACK corresponding to this 30 and yet another duplicate ACK corresponding to 31. So these are the 3 duplicate ACKs. So you know now that 26 is lost. So now you're going to retransmit 26 and again do fast recovery. This is fast retransmit also. So at this point, what will your CWND be? Well, SS thresh will be set equal to 3, which is 7 over 2. This one will be equal to 3 plus 3, which is 6. So at this point, as far as the sender is concerned, how many outstanding packets are there? Right, 26 to 32. Then again, another dupack comes as a consequence of 32. Now, would you send any packet? So this does make CWND equal to 7, but there are already 7 outstanding packets, so you cannot send any packets as a consequence of this. There are no more dupacks coming because 32 was the last packet. The ACK that will come next is as a consequence of this 26, and that is going to ask for what packet? 28. Are there any more packets in the pipe at this stage? None, right? So at this point, again, you get out of fast recovery and set your CWND equal to this SS thresh value, which is equal to 3. At this point, if you see, there are no more ACKs coming. The sender is stalled. The clock is lost. That is the self clock. So how would you recover the loss of this packet 28 then? Basically, you have to recover only through timeout. So at some point it will time out and you're going to resend this particular packet 28. At this instant, you again have to cut your congestion window by half, where you set CWND equal to 1 and this your SS thresh. If it is max of this versus 2, it will take on the value 2. So once you get an acknowledgement for this, which hopefully will acknowledge all the packets up to 32, rather it will ask for 33. Your CWND now is equal to 2, which means you can send 2 more packets, and as a consequence of this you can do 33, 34, and after this point, once you get an ACK for this, CWND is 3, which is greater than SS thresh. So from this point on, congestion avoidance kicks in, and that is how you probe the network for additional bandwidth. So as you can see, TCP Reno doesn't do too well with multiple losses in a window. Like here in 26 and 28 were lost, it had to time out to recover. In case only 14 was lost, you would have done fast retransmit, and as soon as this acknowledgement for 14 had come, you would have acknowledged all the packets up to 32, and from then on you would have done congestion avoidance to slowly probe the network. Things would have been much better. So that's it with respect to the TCP Reno example. As we have seen, TCP Reno doesn't do very well. There are multiple losses per congestion window. It does great if there is a single loss per window. But when there are more, it kind of stalls. That is, it doesn't work for high loss rate scenarios. So to compensate for that, there is a new version of Reno called TCP New Reno. So in high loss rate scenarios, this can handle multiple losses for congestion window better. Not just this version, there are many versions of TCP. Another is called TCP Vegas, where you're using the packet delay to signal congestion rather than these duplicate ACKs or timeout intervals. Then there is TCP selective acknowledgements. We have seen selective acknowledgements as part of the sliding window protocol earlier. So here you're specifically conveying where are all the holes as part of the receive window. Thereby the sender can retransmit those missed segments more efficiently. Here, when you use cumulative acknowledgements, you are going to do one retransmission at any given time, and you are doing this based on cumulative acknowledgements. That's not very efficient. Don't worry, I'm not going to cover any of these other TCP versions. So to summarize, TCP Tahoe is the simplest of all the versions. It is based on go back N, which includes slow start and congestion avoidance. In some places, they include fast retransmit as also part of TCP Tahoe. But what's in a name? When I ask any questions about Tahoe, I will specify clearly what are the mechanisms it employs. So the problem with TCP Tahoe is that the loss recovery is slow and it drains out the pipe during the timeouts. Reno addresses these problems via the fast retransmit, where it recovers losses via duplicate acknowledgements, and it uses this fast recovery to prevent the draining of the pipe. Up ahead, we will put everything in the context of the sliding window protocol. We will also address flow control and a few other miscellaneous issues.